According to physical models, at the beginning of the universe, shortly after the Big Bang, there were exactly equal amounts of matter and antimatter. However, matter and antimatter annihilate each other, so the universe should have destroyed itself immediately. Something must be wrong with our models. I traveled to Switzerland, to Cern, to get to the bottom of this great cosmic mystery. Please let me know in the comments if you would like to see more reports like this, and I will try to organize them more often this year if there is interest. And subscribe to the channel if you don't want to miss out. Every new subscription really helps me to continue my work here. Cern is not a place you just visit on a whim. It's a place you enter with the feeling of standing at the frontier of our knowledge. Here on the outskirts of Geneva, thousands of people from all over the world are working on questions so fundamental that they seem almost philosophical. Why does matter exist at all? Why does our universe consist of what we see and not its perfect counterpart? My visit took me deep into the heart of this research, away from the familiar headlines about the Large Hadron Collider, to an area that is often less visible but perhaps even more mysterious: antimatter. Antimatter is not a science fiction concept. It is real, measurable, producible, and at the same time extremely unruly. It disappears immediately as soon as it comes into contact with normal matter. And yet researchers here at Cern are able to generate, store, and manipulate it in a targeted manner and even conduct experiments with it. I was allowed to see places that normally remain closed to the public: the Antimatter Factory with the Antiproton Decelerator, the ELENA ring, and the AEgIS experiment, which asked one of the most fundamental questions in physics. Does antimatter fall in the same way as normal matter? Is it affected by gravity in the same way as its counterpart? I was accompanied by one of the leading minds in this field, Professor Carsten Welsch from the University of Liverpool, who conducts research here at Cern. Together with his team, he's working on experiments that challenge our understanding of gravity, symmetries, and the beginnings of the universe. In this video, I take you on a journey to a place where the smallest particles are expected to provide answers to the biggest questions. Cern's Antimatter Factory is not a single laboratory, but a highly complex interplay of accelerators, storage rings, traps, and experiments. Its goal is clearly defined and yet extraordinary: the controlled creation and study of antimatter. But what exactly is antimatter?
Everyone knows what matter is, or at least everyone should know, because I hope all viewers are made of matter. But what is antimatter?
Well, the special thing about antimatter is that you don't find it freely in the universe. It's kind of like a mirror image of our normal world, and when antimatter and matter meet, the two particles annihilate each other and turn into pure light, and both disappear. That means you can imagine it as a particle and an antiparticle like the mirror image of one another. And the special thing is, when the two come together in the same region of space, both disappear. Antimatter was postulated in the 1920s by Paul Dirac. At that time, he tried to reconcile general relativity with quantum mechanics, and in doing so, discovered an equation. And the equation had two solutions. One solution described a matter particle, the other solution an antimatter particle, and just a few years later, he actually detected the first antiparticle in an experiment, the positron. And in that case, it was really so that people knew exactly how an electron behaves in a magnetic field. That means they knew precisely which paths it would take and how it would curve. And suddenly they saw a particle that did exactly the opposite. That means it had exactly the same orbital radius, exactly the same trajectory, but the curvature was in the opposite direction, like an image and its mirror image, and that's where the terms matter and antimatter come from.
Here in the Antimatter Factory, antimatter is not created by chance. It is produced in a targeted manner by firing high-energy protons at a metal target. At that moment, particle cascades are created, including antiprotons. However, these newly created antiprotons are much too fast and much too energetic to be used directly for experiments. This is where the real challenge begins. Antimatter cannot simply be touched or placed in a container. It must be captured using electric and magnetic fields without ever colliding with normal matter. Any error, any impurity in the vacuum would destroy it instantly. The Antimatter Factory is therefore one of the most technically sophisticated facilities in the world. Ultra-high vacuum, extreme precision, the finest control over energies that are millions of times smaller than in classical particle experiments. Several experiments work hand in hand here: alpha, G-bar, base, and AEgIS. They all pursue different questions, but they share the same infrastructure and the same dependency: a reliable, controllable source of cold antimatter. What makes this place so special is not only the technology, but also the change in perspective. While many areas of particle physics strive for ever higher energies, here it is about the opposite: slowing down, cooling, control, patience. Antimatter research is not a hunt for spectacular particle traces. It is precision work at the limits of what can be measured, and that is precisely why it is so valuable.
Yes, it really is a very special place, not just at Cern, but for science worldwide. It's the only place where antimatter is deliberately produced for low energy precision experiments. That means we're really trying to understand what antimatter is, how it behaves, and especially how it can be compared to the matter we normally know.
This place here plays a very special role in these experimental confirmations. You just told me that some really major breakthroughs in antimatter research have already been achieved here.
Yes, quite regularly, actually. The first time was back in the late 1990s, in 1996, I believe, when Walter Ehrlich and his team actually produced real antimatter in the lab for the first time, antihydrogen, a real atom. So not just a positively charged electron or an antiproton, but an actual neutral atom that was created in the laboratory. And back then, it was a media hype like Cern had never seen before. It really made headlines all around the world. Everywhere people were writing that Star Trek reality had now been brought to Earth, and there was a real hype about science, the likes of which had never been seen before in basic research. And that continues to this day. So I really think you can say that antimatter research is one of the sexiest fields in science, because you can immediately tell the moment you mention it, people react to it. Everyone has some idea that antimatter is important, whether it's from Star Trek, from Star Wars, but no one really knows what it actually is. And then to find out that real scientific research is actually being done with it here is truly fascinating for most people.
The Antiproton Decelerator is the heart of antimatter research at Cern. Its task sounds simple, but it is anything but trivial. It slows down antiprotons very slowly. I walked through this tunnel with appropriate reverence and examined this incredible apparatus. Once antiprotons have been generated, they have energies in the range of billions of electron volts. For experiments such as AEgIS, which we will come to later, these are astronomical values. The AD reduces this energy in several steps by orders of magnitude to a few mega electron volts, but even that is not enough. That is why ELENA was built. The extra low energy antiproton ring. ELENA is a comparatively small storage ring, but its significance is enormous. It further reduces the energy of the antiprotons to only about 100 kiloelectron volts, a range in which antimatter can be efficiently captured for the first time. Why is this so important? The slower an antiproton is, the greater the probability of storing it in electromagnetic traps. This means fewer losses, longer measurement times, and more precise experiments.
Even though this is an accelerator lab, we first have to slow the particles down. And that's a challenge, and we do it in several phases, which we were fortunately able to see in detail today because we had full access. That means we first went to the Antiproton Decelerator, a ring where we capture the antiprotons and cool them down. So we create a better beam and slow them down, and quite dramatically at that. We slow them down by a factor of 1,000 and then move them into an even smaller ring, ELENA, the extra low energy antiproton ring. And in this ring, they are slowed down even further to just 100,000 volts of energy. And that's an energy level where we can actually do something with them. Why? In the end, we want to somehow capture the antiprotons. And to capture them, we need a trap. A trap is essentially a vacuum chamber with an electric and magnetic field inside. And our antiprotons fly into this chamber, then hit a potential barrier of 100,000 volts and are sent back as if by a mirror. Then we switch on a second potential, and just like that, we've trapped our antiprotons between these two potentials. And this voltage that we can switch on is technically limited to about 100,000 volts. And that's why we first have to slow down the beam so much. For that, we need the AD, and for that, we need ELENA. And we were able to take a look at all of that today and walked around to see how exactly this beam actually gets into the experiments.
ELENA has fundamentally changed antimatter research at Cern. Today, experiments receive many times more usable antiprotons than before ELENA. What used to take days can now be done in hours. However, the technical implementation is extremely challenging. Low energies also mean increased sensitivity to interference fields, instabilities, and even the smallest irregularities in the magnetic field. ELENA is therefore a masterpiece of accelerator physics. This impressively demonstrates that progress in basic research is not only the result of big ideas, but also of technological precision down to the last detail. But the really exciting work only begins after the energy of the antiparticles has been reduced in ELENA. That's when the concrete experiments begin, aimed at unraveling the mysteries of antimatter. One of these experiments is AEgIS. AEgIS is one of the most fascinating experiments at Cern because it asks a seemingly simple question, the answer to which could shake our worldview. Does antimatter fall in the same way as normal matter? Based on what we know, it should. General relativity theory states that gravity acts on mass and energy, regardless of whether it is matter or antimatter. However, this assumption has never been directly tested. AEgIS aims to change that.
We also saw nicely on the board and live, so to speak, that the antimatter can then be sent on to various experiments. So once we've created it, captured it, and slowed it down, we could direct it to different collaborative experiments, and one of them is AEgIS. You're playing a leading role in that, I would say. What exactly are you trying to find out there?
Yes, the big question that drives us in the antimatter community is essentially, why are we here? Why do both of us exist? Why does Cern exist? Why does the universe exist as we know it? Because according to the most general theory we have in physics today, the standard model of particle physics, matter and antimatter, should have been created in exactly equal amounts during the Big Bang. That means if at some point in time there was just as much matter as antimatter, what should have happened is that the two would meet, annihilate each other, and only light would remain. Thank goodness that's not the case, because otherwise we wouldn't be able to talk to each other right now. But we simply don't understand why. That means there must be some very fundamental differences between matter and antimatter. And all the experiments here at the Antimatter Factory have in common that we're trying to find those differences. That means we take some of the most precise experiments in the world and perform them on antimatter particles like antihydrogen. So we do spectroscopy and check whether the energy transitions in the antiatom are exactly the same as in the corresponding atom. We look to see if there are any intermediate states that might be slightly different, or in the case of AEgIS specifically, we investigate the question, what happens to antimatter in the Earth's gravitational field? So does Newton's anti-apple also fall down, or does it perhaps go up? And these are simply all questions that in the end can only be addressed and answered experimentally, and that's our task here.
The experiment produces neutral antihydrogen, i.e. bound systems of antiprotons and positrons. Neutrality is crucial because charged particles would be dominated by electromagnetic fields, not gravity. The trick is that antihydrogen is generated as a horizontal beam. As it moves forward, Earth's gravity acts perpendicular to it. High-precision detectors can be used to measure how strongly the beam is deflected downward. This sounds simple, but it is one of the most difficult experiments in modern physics. Any disruptive factor, any residual electric field, any vibration can distort the result. And that is precisely why a measurement is so valuable. Even a tiny deviation from the expected behavior would have enormous consequences for the equivalence principle, for symmetries in nature, perhaps even for our understanding of the cosmic matter-antimatter asymmetry. AEgIS exemplifies the power of basic research. Great discoveries often arise from simple questions if one has the courage to ask them experimentally. And this year, we could witness a real scientific sensation here.
Maybe you could explain in more detail how this works technically. So we want to measure the gravity of antihydrogen. How do I do that? Do I take an antihydrogen particle and let it fall? How exactly does that work? Yes?
In the Middle Ages, people did drop experiments by climbing up a tower and dropping something from it. That's much more difficult with particles. That means it's really an enormous challenge to measure how fast something falls and whether it might fall a little differently. In our experiment, we generate a beam of antihydrogen. That means we have a beam that initially moves essentially horizontally and then falls, or perhaps it doesn't. And we measure that with a so-called Moiré deflectometer. This is an apparatus that's about 2 meters long and essentially observes a pattern that tells us how much this beam is being deflected. That means whether it falls and also how much it falls. And this is an experiment that is very difficult to carry out. So we start with antiprotons, have to combine them with positronium, which brings its own challenges. We only had a major breakthrough in 2024, when for the first time we managed to obtain this positronium. To be able to cool them with lasers, then superimpose them, create this antihydrogen beam from that, and then carry out this measurement. That is exactly our program for next year.
Antimatter is therefore not an exotic fringe topic. It is the key to understanding the universe. Because after the Big Bang, matter and antimatter should have been created in equal amounts and destroyed each other. The fact that we exist today means that something is not quite right, and the experiments I have seen here at CERN are attempts to understand this imbalance. Not through speculation, but through precise measurements, through patience, through technology at the limits of what is feasible. I was really impressed by this visit, not only because of the gigantic facilities, but also because of the attitude behind them. This is not about quick answers, but about clean questions. Not about sensationalism, but about knowledge. Antimatter shows us how much we still don't know, and that's exactly why this research is worthwhile. And who knows, maybe this year, thanks to the AEgIS experiment, we'll have an answer to the biggest question in the cosmos, and what if not?
So, of course, we hope that some kind of distinction will be found there. What if not? If it turns out, okay, the gravitational measurement shows that antihydrogen behaves just like hydrogen, we can check that off. Now we know. What happens next?
Well, we actually have a very large experimental program that includes these gravitational measurements, but is not limited to them. That means we also have exciting measurements planned for exotic states of positronium, so-called Rydberg states, where we can precisely measure this positronium, which is a particle made up of a positron and an electron. So we are envisioning measurements like that as well. We're also currently looking at three-body problems where we want to study the recombination of certain particles. That means we have a whole range of experimental ideas that we want to work through one by one.
I'll keep you posted, and by the way, during my visit to Cern, I also visited another exciting place, the ALICE detector, a gigantic structure 60 meters underground. If you don't want to miss the video about it, subscribe to the channel now, and if you want to dive even deeper into the fascinating world of research, click on the video displayed in the upper right corner. There you'll find out whether antimatter might soon enable futuristic propulsion systems that will allow us to travel to the stars. It's very exciting. We also talk about NASA's fascinating concept of the helix propulsion system, which could fly to Alpha Centauri in a realistic time frame for humans. Otherwise, I'd say see you in the next video. Take care, everyone.